Moment area can be a very efficient method for predicting slope or deflection in a beam if we need only that information at one point. The key concepts we're going to use in this example are generating M over EI diagrams, using the moment area method to predict vertical deviations, and expressing vertical deflection at a point as a combination of vertical deviations. And here's our problem. It's a simply supported beam, pinned at A, roller at B, with a cantilevered end and a couple moment applied at end C. That's our only applied load. This is the same problem that we used for the double integration example and we use in the conjugate beam example. EI is constant along the beam, and we want to predict vertical deformation at point C. And here's the approach we'll follow. Our first step will be to approximate the answer. So that we have something to compare against after we perform more lengthy calculations. Then we'll calculate reactions, because we need to be able to construct the M over EI diagram for the beam, and we'll need the reactions in order to do that. Then we'll outline our plan for finding the vertical deformation at C, because that affects what part of the M over EI diagram we use in the moment area method, which vertical deviations we calculate. And then step 5 is to actually make those calculations. Now the moment area method doesn't give us the deflection we're looking for directly. It gives us vertical deviations, and that's why the plan for finding delta C, we need to know how to combine those deviations in just the right way to get the vertical deformation we're looking for. And then we'll compare with the approximation. To make sure we have a reasonable result. Step 1. We always begin by approximating the answer if that is possible. So we have something to compare against at the end to make sure we have a reasonable result. So let's take a look at the deflected shape we expect. Well, if we focus on this cantilevered end, if we considered just that cantilevered end subjected to the couple moment, we'd get a deflected shape that looks like that. And that vertical deflection is already available in a formula in the front cover of our book. Cantilever with a couple moment, and there's peak deflection. Well, this situation is fixed, so the slope is 0 at B. Our real situation, the member arches between A and B, which means there's a rotation at B, so this deflection is going to be bigger than this approximate answer. So we're going to underestimate our solution or our prediction for the vertical deflection at C, and it's a minus the moment squared, or the moment times the length squared, because this couple moment is drawn in opposite direction from the one in the front cover of our book. So we have a minus 50 kilonewton meters times the length of our cantilever here, 6 meters, squared, over EI, 2 EI. Combine that to get a minus 900 kilonewton meter squared over EI. Now let's calculate reactions. Because we'll need those in order to construct the M over EI diagrams. We have a vertical reaction at A, vertical reaction at B, and a horizontal reaction at A. At some moments about point B, we can choose either direction to be positive, whichever suits our bookkeeping better. I'll choose clockwise as positive, since each of the components, AY, and the couple moment applied at the end, are both in a clockwise direction. Solve that for our unknown reaction at AY, we get a negative 8.33 kilonewtons. It is not up like we originally drew. Now we'll sum forces in the Y direction. We'll choose up to be positive for our summation. We get the negative 8.33 kilonewtons at AY. We add BY. BY is a positive 8.33 kilonewtons, so it is up as we drew it. Now we're ready to construct the M over EI diagram. And to do that, we'll start by constructing the shear diagram. For our beam. We calculated that there is a negative shear, or a downward applied jump at end A of negative 8.33 kilonewtons. There's no distributed load applied from A to B, so the shear diagram must be constant. There's a vertical jump of 8.33, so we have a negative 8.33 plus 8.33. That closes to 0. Then there is nothing, no distributed load, or no concentrated loads, no reactions from B to C. So our shear diagram closes properly. Now our moment diagram in units of kilonewton meter. Point A is pinned, so it starts at 0. The shear is constant and negative, so we get a linear moment diagram heading in negative direction. It starts at 0. The change will be the 8.33 kilonewtons times the 6 meters, which is the area in this rectangle, and we'll get a negative 50 kilonewton meters. Well, then we have no shear, so the moment diagram must be constant. And then we have an applied couple moment. It's clockwise, so we get a positive jump. We go from negative 50 plus 50, that equals 0, so the moment diagram closes to 0 as we would expect. Now, divide that by EI. EI is constant along the length of the beam, So my m over EI diagram will have exactly the same shape as my moment diagram. It's just that my magnitude has changed to minus 50 kilonewton meters over EI. Before we spend time calculating vertical deviations, let's have a plan for finding the vertical displacement at C so we can figure out which vertical deviations we need to calculate using moment area. So step 4. Our plan for finding the vertical deflection at C. Well, we said that we anticipate our deflected shape to be such, which means this is the quantity we're looking for. Well, moment area tells me the distance, the vertical deviation between a tangent line and a point on the deflected shape. So if I use moment area at this point, I can get the vertical deviation from the tangent line coming off of point A to point B. And using similar triangles, I can get delta prime from this quantity, because this is along the horizontal axis. This overall height I can get from moment area. It's the vertical deviation from the tangent to at point A to the deflected position at C. So we can find the vertical deflection at C by taking this quantity found by moment area and subtracting delta prime, and knowing that we can find delta prime from similar triangles, this height over 6 meters has to be equal to delta prime over this distance, which is 12 meters. So delta prime is twice the vertical deviation from the tangent at point A to point B, to the deflected shape at point B. So we're going to get the vertical deflection at C from the vertical deviation C relative to A minus 2 times vertical deviation B relative to A. Now we're ready for step 5. Find the vertical deviations. And to do that, we need our m over EI diagram. Which has this shape, and we said the magnitude here is minus 50 kilonewton meters over EI. And we'll break this into two shapes, the triangular shape and the rectangular shape. Now to find TB relative to A, it's going to be x bar, the distance from B to the centroid of the m over EI diagram, and the integral from B to A of the m over EI diagram. And so the centroid is here. X prime B relative to A will be this quantity, which is going to be 2 meters. So we have equals 2 meters. Then the area underneath the m over EI diagram, it's a triangular region, so we have 1/2, the base, which is 6 meters, and the height, which is a minus 50 kilonewton meter over EI, and we get a negative 300 kilonewton meter cubed over EI. The negative means that the deflected point B is below the tangent from A at a distance of 6 meters, or above point B. Now let's find the vertical deviation of point C from the tangent coming at point A. Again, this is x bar. This time it's the integral from C to A, m over EI diagram. We'll divide this into two parts. This part, the rectangular shape, and this part, the triangular shape. So for part 1, our x bar, C relative to A, is going to be the 6 plus 2 is going to be the 8 meters, and our centroid for the rectangular shape will have an x bar of half the width of the rectangle, or 3 meters. So we have x bar to segment 1 is the 6 meters plus the 2 meters. Then the area of the triangular region, the 1/2, 6 meters minus 50 kilonewton meters over EI. We add in this x bar, 3 meters, times the area of this rectangle, 6 meters, times the negative 50 kilonewton meter over EI. Put those all together, and we get a negative 2100 kilonewton meter cubed over EI. Now we're ready to predict the vertical deflection at C. From our plan, we said the vertical deflection at C will be the vertical deviation of C from the tangent coming off of A minus 2 times the vertical deviation of point B from the tangent coming off of A, and that equals a minus 2100 kilonewton meter cubed over EI minus 2 times a negative quantity, 300 kilonewton meter cubed over EI, which gives me a total of negative 1500 kilonewton meter cubed over EI, and the negative means it's down. So our predicted shape was that we expected down. This quantity is negative, it is down. That's a good sign. Step 7, compare with our approximation. Approximation we calculated was 900 kilonewton meters cubed, negative 900 kilonewton meters cubed over EI. Remember that we said that would be an underestimate. And we just calculated negative 1500 kilonewton meters cubed using moment area. This is a larger quantity than our underestimate, not by orders of magnitude, so it's pretty reasonable to say that our prediction is a reliable quantity. Note, this quantity is no different than the magnitude we got by double integration. Let's review the process we followed to get to our prediction of the vertical deflection at C. We started by drawing our anticipated deflected shape, or also called the elastic curve, and we said if we consider this to be fixed and just have the couple moment on the end of a cantilever, we can get a lower bound estimate of the vertical deflection. And we did that using formulas in the front cover of our text. We then calculated the reactions and used those to construct the M over EI diagram. Before spending time applying the moment area method to find vertical deviations, we planned out how would we combine certain vertical deviations to get the vertical deflection at C that we were looking for. So we noted that if you draw the tangent from A all the way out, this overall height, the vertical deviation of point C from the tangent coming off of A, includes the delta C we're looking for. And if we calculate the vertical deviation at B from the tangent coming off of A, we can get this piece from similar triangles once we know this one. So we came up with our plan for predicting the vertical deflection at C. We then found the two vertical deviations we needed using moment area, solved for delta C, and compared with our approximation. The quantity we calculated was bigger than our underestimate, but only by about 50%, and so that's a reasonable markup considering the simplifying assumption we made. So we have reason to believe that our prediction of negative 1500 kilonewton meters cubed over EI is a reasonable prediction for the vertical deflection at C. Well done.